So yeah, what I will talk about is a method that we proposed a few years ago, aimed at kind of capturing certain dynamical features of strongly interacting many-body systems. So it was originally proposed in this first paper, and then we had a second paper, which is kind of a theory background, trying to understand when and how this works. And then in the last part of my talk, I will talk about various ongoing projects that are about applying this method to various problems and see what we find in terms of physics. So yeah, those are roughly the three parts of my talk. First, I'll give a bit of introduction to what the actual problem is that we are trying to solve, then explain how this method works, and then I go on to applications to various physical setups. So the basic background is looking at transport in quantum many-body systems. So transport is kind of one of the most fundamental way that we probe what happens in a physical system. Like you whack it with something and see how it relaxes, or you couple some leads to it and see how it responds. And one thing that's interesting about this is that it kind of distinguishes between fast and slow degrees of freedom in your system. There will be some degrees of freedom that relax very quickly to some final steady state or an equilibrium state, but there will be some very slow modes that take a long time to relax. And those usually contain interesting universal physics. And one of the main sources of such slow modes is the presence of conservation laws. If I have some conserved quantities, then they cannot relax locally. They have to be transported to the system, which takes a long time, so that gives you these slow modes, and they show up in kind of long time, long wavelength behavior of the system. Okay? So what can we say about those? And in generic systems that don't have a lot of conservation laws, they are kind of at high temperature, strongly interacting, there are no long-lived quasi-particles, there's a very nice effective theory that describes what happens on these long timescales, which is hydrodynamics. So the basic physical picture of it is that even though it takes a long time for your system to reach equilibrium globally, it reaches some sort of equilibrium state locally. I start with some far from equilibrium state, but if I look at some kind of fluid cell, which is big compared to microscopic length scales in the system, but small compared to the whole system, it will quickly reach some local equilibrium state. And because it's in equilibrium, it will be described by a few parameters. It will be described by temperature, chemical potential, so on, which will be determined by the conserved quantities. And after that, there is some slow relaxation, which is hydrodynamical, depending on this profile of temperature, chemical potential, and so on. And that only has some effective description that only has a few parameters in it. But so this is a very nice theory as an effective description, but there is kind of a big question here, which is how to connect this effective description to the actual microscopic dynamics that goes on. At first sight, these are very different. Microscopically, you have lots of degrees of freedom. There's some reversible dynamics, which might be quantum mechanical. On the other hand, the hydrodynamic description is very different. You only keep track of very few degrees of freedom, and you have some dissipative description, which is effectively classical, even if your underlying system is quantum. So the question is how to connect these in practice. And that's also a computational question. So hydrodynamics gives kind of the general form of what happens, but there are concrete numbers that show up in hydrodynamics, which we would want to determine from microscopics. And a slightly different perspective on the same question is this kind of information paradox. If you think in terms of kind of computational resources that you need to simulate the dynamics. So if I imagine starting some simple initial state in a quantum system, evolving under strongly interacting many-body dynamics, the complexity of this state blows up very quickly, usually exponentially. So the number of bits you need to represent it, the information, the bond dimension, if I want to represent it as a tensor network, grows very quickly, and I run out of resources very quick. But on the other hand, at long enough timescales, again, I should reach this kind of local equilibrium where there should be a simple description of the system. So somehow there is some competition between this growth of complexity and the simplicity that you get at long times, which somehow comes from the fact that even though describing the state exactly is very complicated, you don't need to do that. You only need to keep track of a few parameters in it. So there's a question of how to bridge this gap. And just as a quick aside before going into the details, is that this kind of hydrodynamic transport is relevant to a bunch of experimental settings. So in quantum magnets or cold atomic gases or in some experiments on graphene, you can go to a regime where really you see these hydrodynamic features pop up. Okay, so with that in mind, this is roughly the goal that we're trying to achieve. First of all, we are mostly looking at transport in the linear response regime, in which case you can replace thinking about far from equilibrium initial states, just thinking about dynamical correlations evaluated in an equilibrium state. So you're close to equilibrium, you fluctuate a bit away from equilibrium, and you look at how you relax. And again, so this sort of low frequency, long wavelength behavior of these quantities should be described by some sort of hydrodynamics. And the kind of systems we are interested in, where we are on a lattice, momentum is not conserved, this hydrodynamics is usually just diffusive. So the leading order, the behavior you expect is that if I create a small perturbation, add a particle to a system, it will slowly diffuse out. And how it diffuses will be captured by some diffusion constant, which at the level of hydrodynamics is just some parameter that's there, but it will be determined in practice by features of the underlying microscopic dynamics. So that's the goal, if I want to state it precisely. That given some microscopic Hamiltonian, we would like to determine this diffusion constant with some given precision epsilon. And if I try to do this sort of brute force, just doing some exact time evolution on small systems, or trying to do just a brute force matrix product state time evolution, the resources I would need, the memory or the bond dimension, would blow up exponentially with the inverse error. So the more precise I want it to make, the resources get exponentially bigger. So the claim, which we cannot prove, but we have a fair amount of evidence for, is that this method that I'm going to describe can do essentially exponentially better, something that only grows exponentially with the logarithm of the error.
We have a question.
Yes.
Do you know what the answer is for classical dynamics? There should be some kind of an expression like this, right?
Right, yeah, I haven't really thought about that. I feel like that shouldn't be exponential, or that you should be able to do better, but I'm not 100%.
People have made a point that classical dynamics is plagued by chaos and this and that, and somehow this shouldn't matter, but I'm curious what...
I guess my feeling is that chaos shouldn't matter for this so much, because again, this is some coarse-grained quantity that doesn't necessarily care about precisely following an individual trajectory. Okay, any more questions before I move on to details? Okay, if not, then what I'll do next is describe this method in some detail. So just to reiterate, we want to calculate this kind of unequal time correlation functions in equilibrium. And for now, I'm going to stick to infinite temperature. Later, I will go back to what happens at finite temperature, but it's a bit simpler to think about infinite temperature. And in that case, I can rewrite this as a kind of Green's function or a probability amplitude between starting from some initial operator localized at some site 0, evolving it in time, and we're looking at the amplitude that it ends up as a operator at location x, where this q of x is the local density of some conserved quantity. Okay, so essentially, instead of thinking about operators, we think of them as states or vectors in some double Hilbert space. And in a tensor network language, that just means that instead of dealing with an MPO, you can group its physical legs together to make it look like an MPS. And this has some evolution generated by taking a commutator with a Hamiltonian. So here, this kind of computational difficulty that I talked about shows up in the form that if I take this object and just evolve it in time, the entanglement of this MPS, which is, people call it the operator entanglement, will grow linearly in time. So it will have some profile. It's biggest at the initial location, position 0, but the maximum of it grows linearly in time, so that's an exponentially growing bond dimension. So you very quickly run out of resources. So what we are trying to do is somehow mitigate this problem. And the way to do this is we're going to change the time evolution. Instead of simulating the original unitary time evolution, we will simulate a slightly modified non-unitary dynamics, which is modified in such a way such to prevent this growth of entanglement, but at the same time designed in such a way that these correlations that we care about will not change significantly. So how do we do that? The idea is the following. So first of all, it's useful to introduce a basis in the set of operators that I can use to write any operator as a linear combination of. And the basis we use is this basis of kind of Pauli strings. So I'm imagining a one-dimensional spin 1/2 chain. Every side has 4 operators, identity, x, y, and z. And I can take arbitrary products of these. There's 4 to the L operators for a chain of L sides. And I can use this to write anything as a superposition. And for each of these Pauli strings, I can assign a notion of a size of the string, basically meaning something like how many sides it's acting on. So something like this zx, identity, yx, and so on. This would have size 5 because it has 5 non-identity operators. And we'll use this notion of size as kind of a cutoff. Basically, the picture is that I start with a local operator, I evolve it in time, it becomes increasingly non-local. It will evolve to operators where the size is giant. But those will be less important for the kind of dynamics we care about, because eventually we only care about, if I think of it as like a path integral, we only care about paths where eventually I go back to a local operator. Maybe at some intermediate time, the operator gets very big, but it needs to go back to something local to contribute to the quantity I want to calculate. And the idea is that those paths which get very big at some intermediate time, we expect them to have a small contribution, basically. And I will return to this later, why this is the case. But basically, once you get big enough, it's very unlikely that you would shrink back to a local operator, just because there are so many more big operators, you are more likely to just keep growing. So motivated by this, what we do is we introduce this kind of dissipator, which is a super operator acting on operators. And it has 2 parameters, L star and gamma. So L star is a cutoff in terms of this Pauli length or Pauli size, such that operators that have a size below this will not be affected by the dissipation. So the point of this, one point is that you want your conserved quantities not to be affected. So you have conserved quantities, which are sums of local densities. You want to choose this L star big enough that those will not be affected. And then for things that are above the cutoff, they get hit by a factor which is exponentially small in their length, and this exponent is controlled by some dissipation strength gamma. So if you take gamma to be 0, then this does nothing. If you take gamma to be infinite, then you're just projecting out all your non-local operators which have size larger than L star. And so now what you do is that you kind of intersperse the original unitary evolution that you cared about with this dissipation. So every time delta t, you hit your system with this dissipator, and you get rid of some of your non-local operators. And this has the effect that those contributions where you kind of wander out and spend a long time in the space of large operators, these contributions will be decreased. But because we expect these to be small anyway, the hope is that actually this skill gives a good approximation for the kind of quantities we care about. Okay, so again, if I made delta t 0 and gamma infinity, this would be kind of a hard projection onto just a space of small operators. But in practice, it's useful to kind of soften this and allow some excursions to the space of large operators, just not too much. And in practice, it turns out that only really this ratio of gamma divided by delta t that matters. So even though it seems like you have 3 parameters to play with, it's really only 2. You can fix delta t to be something, and you have gamma and L star. Okay, is this clear? That's the definition of this method. All right. So I've defined this in principle, but how do we actually apply it in practice? So you can do this in 1 dimensions at least using matrix product states. So our initial operator, as I said, is represented in MPS. The unitary part of the time evolution you can do using all sorts of standard methods. Let's say TBD if it's nearest neighbor. And this dissipation actually has a nice compact representation as an MPO with bond dimension L star plus 1. It basically acts like a clock in the internal bond space. Whenever you see a non-trivial operator, you go one step further until you reach L star. After that, you just keep picking up this e to the minus gamma every step. And the very nice thing about this, which makes it useful, is that once you add this dissipation, this will cut off this growth of entanglement that was really plaguing your numerics before. So before I showed you that the entanglement of the operator grows linearly in time, but now, once you switch on dissipation, what you find is that it grows for a while, but then it peaks and comes back down. And now, the maximum entanglement bottleneck that you need to go through will be controlled by gamma. For a given gamma, there is some bond dimension that you will need, but once you have that, you can do this forever. There is no time limitation. And you can also see that the conservation law, how well the conservation law is satisfied, gets better and better, and you can get basically the error down to as small as you want by increasing the bond dimension, which was not the case before, because without additive dissipation, you get truncation errors that destroy the conservation law and will give you the wrong results. Okay, so how do we get a diffusion constant out of this in practice? So now we can use this modified dynamics to calculate correlation functions. And once you have the correlation functions, what you find is that in a diffusive system, they will have some Gaussian profile spreading out diffusively. And then you can just basically see how the width of this distribution grows and fit a line to that to get a diffusion constant. So there is some time-dependent diffusion constant, which is the derivative of how this width grows, which should go to a constant. So testing it out on this non-integrable Ising model, which is kind of a good test case for chaotic dynamics, we indeed see this very nice Gaussian. And what we find is that, so for small systems, you can do exact dynamics, see how the width of this distribution grows. You see it starts growing linearly, but then you get finite size effects. However, using our method, you can see that you can follow this for much longer times, beyond the time that you could do using exact numerics. Okay, and this is this time-dependent diffusion constant. And you see that it changes with this parameter gamma, this strength of the dissipation. So at the end of the day, what you want to do is you kind of want to make this gamma weaker and weaker and see how the dynamics approaches to the actual unitary dynamics that you actually want to simulate. So in practice, the way you do this is something like this, that you fix a gamma, which has the strength of dissipation, you simulate the system, get a diffusion constant out of it, and then you do this for different gamma, make gamma smaller and smaller, and you try to extrapolate back to gamma equals 0, which is the actual unitary dynamics you care about. And if you can make gamma small enough, then you can actually do this extrapolation. Yes?
Is there a theory that tells you why it should be linear in gamma?
Yeah, so we expect that this is sort of analytic in gamma and small gamma. So to leading order is linear, but of course you have to get close enough to gamma equals 0 to actually see that. In practice, we see that sometimes it's better to fit a quadratic to it, that you can get good results or better results if you fit quadratically. But generally, the idea is that it should be kind of analytic in gamma. Yes?
But it can't be analytic in gamma because if you make gamma negative, nothing makes sense. So there's no neighborhood technically around gamma equals 0, which is the point you want, that you can expand your results around.
Okay, that's a good point. Right. Okay, I would have to think about that. But okay, maybe saying it's analytic is not technically correct. But I guess it might still be the case that at least for positive gamma you can expand in gamma. But yeah, okay, I should think about that. That's a good point. Yes.
So, for instance, here you're looking at the energy density.
Right. Yes. Yeah, I should have said that. Yeah, exactly. So here, this model has no constant quantities other than energy. So here we are looking at energy transport. There's a local Hamiltonian density, basically each term in the Hamiltonian, and we are looking at correlations of that.
And in general, you would know a priori what are the relevant degrees of freedom?
Yeah, we assume that you know that you know what your symmetries are, that whose transport you're looking at. Right? Any more questions? Yes.
Maybe another question. So if you keep truncating, with TBD fixed bond dimension, and you reach the same maximum bond dimension with your gamma, right? Are results qualitatively different or no? So is TBD truncation doing the same as your gamma, or is it doing much worse, or comparable job?
Yeah, it's doing much worse. We had a plot on that in our paper, which I didn't put on my slides. But so basically, if you look at this this plot, and you also plot on it what you get by just running TBD with a fixed bond dimension, what you see, it kind of gets to the same times as the largest system size here. This L equals 10 to 1. But after that, it just goes crazy. I think it just sort of flies off somewhere. Because basically what happens is that the conserved quantity is no longer conserved. One truncation errors kick in, and then it's just completely unrelated to what you expect. Yes?
I have a question just to check I've understood. So L star is the truncation length scale, is that right?
Right.
And so in the next slide, you have different convergences with gamma for those different length scales. Do you see a change when you get beyond the thermal correlation length of the long time state?
Well, okay, so far everything I said is kind of infinite temperature, so the thermal correlation length is 0. I'll say later that we are exploring finite temperature, but okay, I don't have anything sharp to say about that yet. Yeah, actually, let me go.
I'm just curious. So you're dropping long strings, but you could also just say that you could convert long strings back to short strings. Because in a way, like if you had a process of measuring some of those guys, so have you considered a dynamics where you kind of like push things back rather than just dropping them?
Well, I somehow would think that that's worse. In some sense, for example, the reason to have this gamma parameter and have kind of a soft rather than a hard cutoff is because one way this can go wrong is if you kind of do a hard cutoff where you just basically make operators bounce back when they get too big. That actually can give you errors because something that wanted to get bigger and bigger cannot, and it sort of bounces back and gives you more contribution than you wanted.
I'm not sure what you mean by bounces. I thought it was just a cliff where you leave the anyway.
Well, so if you made gamma infinity in our case, then you would actually get unitary dynamics in like a restricted space of only local operators. So that's what I mean by bouncing back, that in that case there is actually no dissipation. That's like a quantum Zeno effect. So in some sense, you actually want operators to be dissipated. That mimics what would happen in the absence of a cutoff, where things would just get bigger and bigger, and you would never see them again.
How much are you susceptible to errors due to the assumptions on the diffusion equation that we took? For example, if you have long time tails, do you see that?
Well, so far, this is not assuming diffusion, really. Let's see. Yeah, so we have some estimates of like how big the errors are in time, for example. And I think the upshot is that you would expect that you don't get the subleading corrections correctly, like the subleading things that are subleading to the diffusion equation are kind of the same order as the errors you get from these approximations. So you expect to get the leading order things correctly, but not necessarily the subleading ones. Yes.
So what intuition, why you call that operator dissipation, and why you think short strings are more important than long strings in the thermal limit?
Right. So the intuition is kind of something like this, so in the end you only care about processes where you do go back to something local because you're calculating so you're calculating this sort of return amplitude where you need to go back to a local operator. And so the intuition is that if you kind of post-select on things where you get back to local operator eventually, then the cases where you get very, very non-local in between will be subleading. And we have some sort of theoretical understanding of why that is. Roughly speaking, there are kind of two effects. One is just sort of entropic, that there are so many more large operators than small ones. Once you get sufficiently big, you're kind of unlikely to shrink back. That's like a very unlikely process. Plus, there is some sort of phase cancellation, that these many different paths come with random phases that can cancel. So it's a combination of those two that kind of gives you a small contribution from these paths that we are throwing away.
Okay, let's take just one more question for now, and then allow Tibor to go on with the
Okay.
slides. So one more question over here, I think.
You're truncating with respect to the length of the number of non-trivial Pauli operators. How does that work for fermions, where you have, in principle, also like strings that are,
Yeah,
What is
very
next?
good. Yeah, so indeed, actually, I will show you some ongoing work that we have, which is applying this to fermionic systems, or at least in a case where it's more natural to work with fermions. And then you actually have to modify this dissipation a bit. Then you would want to, instead of counting Pauli operators, you would want to count fermion operators, which ends up giving you a slightly more complicated MPO, but you can still do that. Okay, good. So I'll go on. So yeah, so this is kind of the procedure that you do different gamma and try to extrapolate back to gamma equals 0. And as Andrew pointed out, we can do this for these different L stars. So actually, this L star is also kind of a useful control parameter in that you can do this procedure in slightly different ways and check that you get consistent results. So that's a nice kind of self-consistency check in the method, that the thing that you get at the end is actually physical, is that I do this for different cutoffs, and once I extrapolate, and for large gamma, I actually get very different results, but they all extrapolate back to values that are very close to each other. And okay, this is just illustrating the same point on a different model. This is a two-leg ladder with XY terms, which has a conserved U1 symmetry, total spin Z. And we are looking at the transport of that. And for a number of different parameters, we get nice convergence. Not always, though. So if you can go to parameter regimes where convergence gets worse in practice. Okay, and so I already said this roughly in answer to a question, but let me just say a few more words about why this actually works, or what's the physical intuition. And it's useful to think in a kind of Feynman diagram picture. So you could imagine looking at this correlation function and doing an expansion where there is a term where you just kind of, your local operator just stays a local operator forever, or there are other terms where it stays local for a while, it does some excursion to some non-local, space of non-local operators, comes back. Or maybe it does 2 excursions, or it does 1 big excursion, and so on. And so basically the main object that shows up in this is this box, which is supposed to represent some process where a local operator grows to some operator that is big. It's bigger than L star at some intermediate time, and then shrinks back. And the claim, which we can support kind of both numerically and some analytical arguments, although not a rigorous proof, is that the size of these contributions, when you put the intermediate scale to length L, decays exponentially with L. So processes where you get very big are kind of exponentially suppressed. And this is some numerics confirming this in these 2 different models.
Is there any caveat about conserved quantities for that claim?
Yeah, so we are assuming here that we are looking at 2-point functions of a conserved quantity. This would not necessarily be true if you're just looking at 2-point functions or arbitrary operators. Yeah, you need some sort of separation of scales, that you are looking at dynamics of slow degrees of freedom, and these large operators are much faster. Okay, and we have some further kind of analytical arguments in our second paper related to this. And so going back to kind of how to calculate things and how hard it is, using this exponential decay, if you ask, again, how much resources do I need to get, for example, the diffusion constant with some accuracy epsilon. So it's known from hydrodynamics that you approach the final diffusion constant as a power law in time. So you have to go to some times kind of 1 over epsilon squared. But on the other hand, we can make this cutoff basically logarithmic in 1 over epsilon to get good enough results. And if you put this together, plus use sort of locality that there is some Lieb-Robinson bounds in the system, you get this e to the log 1 over epsilon squared. And you should compare this to what happens if you just kind of naively try to simulate the system without dissipation, then you would find that you're exponential in the time you need to go to, which is e to the 1 over epsilon squared. So it's kind of an exponential speed up here. Yeah?
Sorry, maybe you said this, but how can I see that the diffusion coefficient approaches the effect on the
Oh, that's just kind of known from hydrodynamics, like just using what you know about diffusion. This is exactly the kind of subleading power law tails that you mentioned. That's what you expect. Okay, very good. So in the remaining, I guess I have around 10 minutes. Okay, then I'll okay, good. I'll flash a bunch of slides on various ongoing things that we are working on right now, which are applying this method to various different physical problems.
Could I ask a quick question before you do that? So,
Yeah.
so you had your slide about the thermalization information paradox,
Mm-hmm.
and I guess that decay of the amount of information you need would correspond to reducing the size of cutoff in time through your simulation. Is that actually something you can make more concrete? That how is there some way you can say, well, if we reduce this L star down at later times, we get more, we remain accurate?
Yeah, so we haven't really done that, but we have some, I guess, some indication that we could do that. So if you consider this plot, which is how does the entanglement change in time, you see something that sort of looks like the thing that I showed you before, where you have entanglement going up and down. So the interesting thing is it goes down at long times. It actually goes down to something that's approaching 1 bit. And that's because at long enough times, you're kind of dominated by things that just look like single-side operators, essentially. So you start going back to this pretty restricted space. So at that point, you could probably reduce the cutoff if you wanted to. But the point is you don't really need to do that because the bond dimension cutoff kind of takes care of that automatically. Like you're already, because your entropy is small, you can actually do things efficiently without explicitly.
I mean, I guess that's okay at infinite temperature, but as you go to lower temperatures, it gets harder. And you might
Yes.
like to reduce L on some physical grounds when you are at lower temperatures.
Right. No, that's true. Yeah. So there's something we're exploring, but yeah, I don't have anything concrete to say about that yet. So that's actually a very good segue into my next slide. But yeah, let me just say that all the remaining slides I show are kind of ongoing work. So results might still change, although hopefully I don't say anything that's incorrect. So exactly. One of the things we are exploring right now is this question of what happens as you go to finite temperatures, or for other Tensor quantities, you can introduce a chemical potential. So that's a very natural question to ask. Like everything I said before was kind of infinite temperature, which is theoretically easy, but practically it's much more natural to think about finite temperatures. And so the point to make here is that we do see that things still work as you go to finite temperatures or finite chemical potentials. It gets harder, so it seems things converging properly gets worse and worse, but we can do it. And one practical observation is that one question you have here is whether to evolve the operator itself, or you kind of evolve operator multiplied by the thermal state. And it seems like it's easier to do the second. Yeah, 2 questions, maybe Mike first.
Operator times the thermal state. That is extensively in point strings. How do you define this?
Yeah, so we still use the same dissipator, which will clearly change the state quite significantly. But the question is, does it change? At the end of the day, this thing will be hit by another local operator. So it will pick out only parts of it. And at least in practice, it looks like we can still converge in that. I'll show some more data on the next slide.
Even in that case, if like the first Q is 1, the second operator is something else, you would have the thermal expectation. Because you would have changed the thermal state. So it wouldn't get like a one-point function.
That's right, but I think if you look at it, yeah. No, I think that should one point function should still be okay. I think.
I didn't catch how you do finite temperature. Like, what's the algorithm for finite temperature?
Sorry, can you say it again?
What's the algorithm for at finite temperature? How do you change it?
Right. So we do something fairly simple. We just create the finite temperature state using basically imaginary time TBD in this case. We prepare this density matrix itself as an MPO, and then you could either evolve the operator as before and just multiply them together at the end, or you could do this where you multiply them together at the beginning and evolve that combined object. Good.
That's Q here still. Is the density is not the full concept.
Yeah, no, it's a local density. Yes. Okay, and again, just some data seeing that we still seem to be able to get sort of nice convergence, at least when mu is not too big. And we see that the diffusion constant starts to grow roughly as mu squared at small mu. So as you increase the chemical potential, the system dynamics gets faster and faster, less goes on from diffusive to less diffusive, which is what you would expect physically. Okay. Another thing which also there was a question about is kind of fermionic version of this. And one nice testing ground for testing it out is some weakly interacting Hamiltonians. So something that looks like fermions that have weak interactions that you can tune. So in some non-interacting limit, you have ballistic transport. And as you increase the interactions, you should get a crossover to diffusion. So we looked at this model. Okay, I wrote it here in spin language. But you can Jordan-Wigner transform this to get a system of fermions. And when delta is 0, this is free fermions. But when you switch on delta, it becomes a system of interacting fermions. And there is some staggered potential that we add to make it non-integrable. And so here, we simulated this using this fermionic version, where you truncate not in terms of Pauli's, but in terms of how many fermion operators appear in your operator. And the nice thing about that is that in the free fermion case, the truncation doesn't do anything because you're anyway not creating large operators. So in principle, you can do the non-interacting case exactly, and then you can turn on the interactions. You can still go to very long times to see a crossover, which is indeed what we see, that it goes from ballistic to diffusive at long enough times. And then we try to extract a diffusion time of a crossover time from this. So these are kind of lower bounds on that, because in some cases we haven't gone long enough to actually see a crossover diffusion yet, but we see that it sort of seems to be diverging as we turn the interactions off. And another interesting problem that we looked at a bit is another version of the same XXZ model, where instead of a staggered potential, you had a random potential. So this is a model that people have looked at a lot in the context of many-body localization. And it's known that there are all sorts of interesting features as you turn on the strength of disorder, W, from 0 to infinity. Eventually, this model is expected to become localized, but there's a very interesting regime before it becomes localized, where people have reported numerically that they see a subdiffusive transport regime. You go from diffusion to slower than diffusion before becoming localized. And so we're exploring this regime numerically. And again, with our method, we can kind of go to longer times than previous studies. And one thing that we find is that this exponent that you get, which would give you subdiffusion, at long enough times you see a drift towards more diffusive behavior. So, okay, the things we see are still subdiffusive, but it looks like maybe if you're able to go to infinitely long times, this would actually just cross over and become diffusive. But on the other hand, we see some interesting features that we don't really understand. So if you look at kind of a scaling collapse of the correlation function, and you rescale with square root of time, which you would expect for diffusion, we get a fairly nice scaling collapse. But the scaling function that we find has some weird features. So this should look like a Gaussian for diffusion, but which is correct for values kind of here in the middle. But first of all, you have tails that seem to be falling off faster than a Gaussian. But more notably, there is this strange feature that there is this peak exactly at the origin. When you look at autocorrelations on the same site, they seem to get some anomalous contribution. They still decay as 1 over square root of time, but they don't fall on this scaling curve. And this is a feature that we are trying to understand why this happens. It seems to be doing something or having to do something with a physics of resonances that people have thought about in the context of this kind of not anybody localized but disordered regime, and this is something we are still exploring. Okay, and I think I'm running out of time. This is my last slide. So one other thing that we are doing is a kind of comparison of our method with various other methods in the literature. So there's been a few other things that people have proposed to solve the same problem of calculating transport in many-body systems. And in particular, we are comparing our method to other ones. One is this sort of non-equilibrium steady-state method, where the idea is that you couple your system to baths, you get some steady state with a current flowing through, you measure that current, and you can use that to calculate transport. And there is something called the cluster truncated Wigner approximation proposed by Anatoly Polkovnikov and his coworkers, which is a kind of semi-classical approximation where you kind of simulate small clusters of the system exactly and use some semi-classical approximation of the correlations between the clusters. And, okay, what we find is that in many cases, these give very comparable results, which is a nice cross-check that they're actually correct. But we tried a very hard example, an integrable XXZ chain, which is nice because there's an exact known analytical result for the diffusion constant. So there's something compared to, but it's also kind of the hardest problem because it's integrable. It has lots of structure. And at least it seems to be the case that our method is, while still sort of significantly off from the analytical result, it seems to be getting things more correctly than these other methods following what the analytical curve should be. Okay, so I think this concludes everything I wanted to say. And yeah, I just finish by thanking all my collaborators, Kurt and Frank, who were involved in the two papers that are already published, and all these other folks who did a lot of the numerics I showed in the last couple of slides. And thank you for your attention.
Okay, there's already been a lot of questions, but we could take time for maybe 2 more.
I have a question regarding this assumption that you can throw away long operators. So naively, we would expect that you have, if you don't have many conserved quantities, most of the dynamics.
Use your seat mic, please.
Yeah.
I would naively expect that most of the dynamics will be captured by the long strings, because you have like 4 to the L operator in your small region, and you have like many more in the larger region, or maybe not, right? And I was wondering whether you can track the norm of the operator. So if you can track how much operator is sitting on the smaller strings compared to the larger strings, and it's something that you see constant decaying on some level.
Right, good. So for the first question, that's really depends on what quantity you want to calculate in the end, what you're interested in. So you're right that if I just track this operator as it grows in time, it will be mostly made up by very non-local operators. But the quantities that show up in transport are these kind of autocorrelations where you're only interested in processes where you go back to some local operator at the end of the day. And so there's the picture that even though you have lots of very non-local operators, they are very unlikely to shrink back to local ones. So their contributions to the quantities you calculate are actually small. And for the second question, yes, so indeed, as you apply this dissipator, the norm of your operator decreases. And we actually have some analytical understanding of how exactly that happens, that, yeah, you have kind of a core of the operator made up by local things, conserved densities, and it continuously decays to longer things as a power law. And the numerics kind of follows that.
Yeah, one more question.
Does the dissipating MPO care about the weight of the operator, or just the distance between the left and the right endpoint?
No, it cares about the total weight in the sense of number of sites the operator is acting on.
I see.
So it doesn't care about locality in that sense. So.
I see. Okay. Would there be much of a difference between just the number of non-trivial sites and just comparing the length of the string between the 2 endpoints?
Yeah, that's something we explored a little bit. It didn't seem to make that much of a difference. But I think it would make a difference in some cases. So for example, in these like weakly interacting fermions I was talking about, there it would be important that the free fermion evolution creates processes where you have two operators that can go far away and come back, but there are only two operators. So there, if you were really truncating based on kind of diameter, you would get things wrong. If you use R truncation, you get things right at a non-interacting point, and then you have a good starting point to add in interactions.
We have a question from Huri Zirpur online. Have you verified the effect of L star choices on the late time convergence, e.g. of your diffusion coefficient?
Yeah, so I think that's in some of these plots I showed before. Oh, yeah, I guess my slides are gone. But yeah, so we had these plots where we have results for different L star, and then you continue them back to gamma equals 0, and then the results you get are consistent between different L star.
Okay, actually, one last pressing question from anybody. Did you have one? Or?
What happens if you apply it to super diffusive system?
Right, so actually we also have some results. We tried looking at the isotropic point of the XX or the Heisenberg model. It seems to work well enough. Like we can somewhat push the existing times that people have been able to go to, and it's not spectacularly better, but it seems to, you do gain something, and it seems to get the correct super diffusion.